Hi, Pre-Calc. We're up to Unit 9, Day 7. Today we're looking at some different frequency equations. So this is the last part of our first bit of solving trig equations before we start reviewing and then have a test. But you'll notice that in the very first example, when you're setting up your notes here, that the different frequency that I'm referring to is the number next to theta on the inside. And sometimes that will be a higher frequency of theta, like here we're doubling theta, but sometimes it could be a lower frequency. We could look at cosine of half of theta. And the approach is very much the same. No matter what the change in frequency is, we're going to approach the solving algebraically using the same technique. Well, in order to get a good concept as to what's going on here algebraically, we're going to consider the graphs. And then the graphs, I think, will eventually help us to determine the solutions algebraically. So I want you to compare the following on your calculator, and I'm going to set this up in a moment. We're going to look at just cosine x equals -1/2, so we'll graph -1/2 in y2, and then see how cosine of 2x looks different as compared to y equals -1/2. So if you go to y equals, we're going to go ahead and make sure that we have typed in cosine x first, and then -0.5 in y2. I have my mode in radians, which is, of course, pretty important in these examples. Oops, I actually don't have that, so I'm saying I do, but I don't. Switch it over, and then for the window purposes, I'm going 0 to 2 pi, and then -3 to 3 is a good range of values for cos, because remember, the max output for cos is just -1 to 1 anyway. So -3 to 3 should be good. If I hit graph, here's what we've got. There's cosine x, and then we'll see y equals -1/2 come across, and we get two solutions when we graph them in y1 and y2. And we can find those solutions pretty easily based on what we've done with solving in this unit. We get this graph. Here's y equals -1/2. So we know that in the end, we'll get two solutions. So I want you to make a prediction about what's going on with cosine of 2x here. That if I change the equation, we're leaving, of course, y2 is -1/2. But if I make this cosine of 2x, how does that affect the number of solutions? So if I hit graph, wow, I got now actually 2 cycles of cosine, and therefore when I graph y equals -1/2, we get a total of 4 solutions. So that frequency has something to do with the number of cycles of the graph by the time you get to 2 pi at the end. So that's something that you would have learned last year, but maybe without doing a lot of graphing yet this year is not as familiar to us yet, but we do wind up getting 4 solutions here. So I guess kind of the moral of the story, and there will be exceptions to the rule, is that doubling the frequency doubles the number of solutions. Okay, and that typically holds true. Like I said, there might be some exceptions to the rule, but I guess now the question becomes, how do I go back to this and get those 4 solutions algebraically? And what we're going to do to do this algebraically in terms of steps is step 1, use a dummy variable. So we're going to replace 2 theta with a dummy variable like maybe x, because I can solve cos x equals -1/2 really easily algebraically. And then step 2, we're going to have to use the general solution to find all the other solutions. And what the general solution is it's the solution over the set of real numbers. So remember that these cosine cycles would go on forever and ever and ever and ever and ever. So when I write this as the general solution, if you look back to the day 4 notes, that's really the only time we've practiced with this. But I hope it sounds familiar when we get to that step. Let me go back to our example then, which is that cos 2 theta equals -1/2. Oh, and by the way, let's solve for all the answers from 0 to 2 pi. That's our typical, right? So we'll solve over that interval. So let's see, if I have cos 2 theta equals -1/2, the first thing I'm going to do is I'm going to let x equal 2 theta. Let's use a quick dummy variable there. So then cosine of x equals -1/2. And now we're already up to the step where we ask ourselves, what quadrants is cosine negative in? So cos is negative, all-star trig class in quadrants 2 and 3. So we're going to label the sides appropriately, that -1's the adjacent, hypotenuse is 2, radical 3's would go here. We need the reference angle. The reference angle across from radical 3 is 60, or pi over 3. Halfway around is 3 pi over 3. I'm going fast because we're at a point in the unit where we really got to know this stuff. Okay, so we get x equals 2 pi over 3. That's the solution in quadrant 2. 3 pi over 3 plus another pi over 3 is 4 pi over 3 for the quadrant 3 solution. Now I'm separating these in this pattern because we know that that's the solution for x. But remember, I'm really solving for theta. We have a dummy variable here. Okay. So what I'm going to do is I'm going to now at this point replace with 2 theta. But before I go ahead and do that dummy variable substitution, I'm going to write what's called the general solution. The general solution is 2 pi over 3 plus 2 pi n. Same thing for 4 pi over 3 if we add on 2 pi n, where n is an element of the integers. If you look back to day 4, like I said, we wrote the same exact statement. What happens is the cos curve repeats itself every 2 pi. It's going to see that same pattern again after 2 pi. So if we add on 2 pi n to write the general solution, now I want you to go back and replace x with 2 theta. Same thing over here. 2 theta equals 4 pi over 3 plus 2 pi n. Okay, we're going to start getting solutions for theta in just a moment here. But the first thing I have to do to get theta alone is divide by 2. When you divide by 2, 2 pi over 3 divided by 2 looks weird. So remember, dividing by 2 is like multiplying by a half. And that might be easier to see that when I multiply this by a half, I now become 2 pi over 6, which I know reduces, but I'm going to leave it like that for now. And then over here, this would be, well, half of 2 is 1, so isn't that just pi n there? Similarly, over here, if you multiply both sides by a half, you get 4 pi over 6 plus pi n. So to get solutions for theta, instead of adding on 2 pi, we're actually only adding on pi each time, which kind of makes sense, right? I see one cycle of this graph by the time I got to pi. So the next solution is going to happen another pi later. Instead of adding on 2 pi every time, the solutions occur a lot faster. They occur only after adding on pi. So here's how we're going to generate the solutions. First, you're going to do n equals 0. And when n equals 0, you want to be getting 2 pi over 6, and then you get 4 pi over 6 as answers. Okay, so that's the first part. Plug in 0 for n. Because remember, n can be any integer. But we only want to plug in values for n that would give me answers from 0 to 2 pi. All right. So then what I'm going to do, I'm going to plug in n equals 1. And when I plug in 1 for n, it becomes 2 pi over 6 plus pi. Here's what I think is going to be a great thing for us to do. Why don't we write these with common denominators and make those 6 pi over 6? So let's see, n equals 1 would get me 2 pi plus 6 pi, which is 8 pi over 6. And over here, 4 pi plus 6 pi, which is 10 pi over 6. So we get 2 more answers. And how do I know when to stop? I should stop when I get to 2 pi. I don't want to get any answers that are bigger than 2 pi. Well, if we were paying attention, we know that there's only 4 solutions. So these 4 answers right here are the only answers to this equation. But let me show you what happens when n equals 2. If you plug in 2 for n right here, you get 2 pi plus 12 pi, which is 14 pi over 6. And how do I know that's too big? Well, 14 over 6 is a number that's bigger than 2 pi. So what you'll see me do in these questions is when I get to this stage, I usually write what's called a limit. And the limit is whatever 2 pi is with a denominator of 6 in this example. So the limit would have been 12 pi over 6. If I get 12 pi over 6, that's 2 pi, and then that's too much as an answer. So if we set a limit for ourselves, we'll know when I plug in values of n, if we get an answer that's above the limit, that we should stop plugging in values of n. Okay. I know there's a lot thrown at you in number 1, but I promise as we do a few more, we're going to get used to this process. So let's kind of go right into another example here. We're going to solve for number 2, sine of 3x equals negative radical 2 over 2. Okay. Now you might remember a little bit about what the graph of sine x looks like. Sine x looks like that. But when you triple the frequency, what happens is by the time you get to 2 pi, you see that once, twice, 3 times by the time you get to 2 pi. So therefore, if I want to know when does sine of 3x equal negative radical 2 over 2, which by the way is a negative decimal somewhere, it's going to happen once, twice, 3, 4, 5, 6 times. There are 6 solutions to this equation. which kind of makes sense to me because I know that sine equaling, sine of a value would equal negative radical 2 over 2 in 2 locations. Sine is negative in 2 quadrants. So if I triple the frequency, we get triple the number of solutions. Okay, let's get started by doing a dummy variable. Let a equal 3x. So therefore, sine of a equals, I'm going to do something else that's sneaky here as well, but we've seen it before. I'm going to write negative radical 2 over 2 as negative 1 over radical 2. It's going to make life a lot easier for us if we kind of unrationalize that. So this way, when I ask you where sine is negative, which is quadrants 3 and 4, and then we label the sides as opposite over hypotenuse, opposite over hypotenuse. If I had stuck with these original side lengths, although it's still a reference that's the same, it's tougher to identify what that reference is when I'm not using 1s and radical 2s, right? And those would be these other sides here. Okay, so let's see what we've got for our reference angle. 1, 1 radical 2 is the pattern for a 45 triangle, so the reference is pi over 4. So halfway around is 4 pi over 4, full circle would be 8 pi over 4. All right, here are my solutions. Ready? A would equal 5 pi over 4 if I'm in quadrant 3, and angle A would equal full circle minus pi over 4, so that's 7 pi over 4 if I'm in quadrant 4. That part you should be pretty okay with. Sine A equals negative 1 over radical 2 has these two answers. But from there, since this is a different frequency equation, we have to add on the general solution, which, like I said earlier, is plus 2 pi n. Do you have to write n as an element of the integers? I'd like you to remember that. It's a small part of the problem, but what we're saying is we're defining n to be any integer value, which could be negatives, but mostly we're going to be using positives to plug in so that I can generate all my other solutions. All right, here we go. So then remember that a is really 3x. So we're now going to go ahead and replace a with 3x so that we can figure out what values of x would satisfy the equation. Okay, and you don't have to carry this n as an element of the integers down every time. All right, now remember what I did earlier. Instead of dividing by 3, I think it's going to probably look nicer if you multiply both sides by a third so that you get x equals, when I multiply this by a third, 5 times 1 stays 5 pi up there. 3 times 4 is 12 in the denominator. This would be plus 2 pi n over 3. All right, similarly over here, you would get x equals 7 pi over 12 plus 2 pi n over 3. Okay. You're eventually going to get to a point, by the way, where you have to add these fractions together. So it's to your benefit to make a common denominator at this stage of the game. So to make a common denominator in both cases, the common denominator is 12. So I'm going to multiply this by 4 over 4. And then that will just make my job that much easier when we go to start plugging in values for n in just a minute. Same thing over here, 7 pi over 12 plus 8 pi n over 12. Okay, we're now up to the stage where we can plug in, let's start with n equals 0. When I plug in 0 for n, you get your initial solutions of 5 pi over 12 and then 7 pi over 12. There's 2 of your answers. Now we're going to move on and plug in n equals 1. When you plug in 1 for n, 5 pi plus 8 pi up here is 13 pi over 12. Same thing over here. 7 pi plus 8 pi is 15 pi over 12. Now we have 2 more answers. When should I stop, by the way? Let's talk about what that limit is. We're looking at things that have a denominator of 12. So when I put 12 in the denominator, what should I put up in the numerator to get an answer that would reduce to 2 pi? Well, 24 pi over 12 is equivalent to 2 pi. That's our limit in all of these questions. We don't want to get answers beyond 2 pi. So I know I should stop if I get an answer that's bigger than this. Well, I'm not there yet. Let me keep going. What about n equals 2? If I plug in 2 for n, this becomes 16 pi. 5 pi plus 16 pi is 21 pi over 12. All right, keep going over here. If n equals 2, 8 times 2 is 16. 16 and 7 is 23 pi over 12. We're pretty close to the limit. Am I going to reach the limit if I get to n equals 3? I hope so. I'm running out of space. If I plug in 3, we get 8 times 3. 24 plus 5 is too big. 29 pi over 12. That exceeds this limit. So therefore, these are the 6 solutions to this equation. And we knew we were going to get 6 from the start. But to prove to you that, yeah, that plugging in n equals 3 is going to go just beyond 2 pi there, these are the 6 answers we should come up with for an example like this. Okay. All right. Hopefully after walking through that one, you feel a little bit better. I am going to try just one more with you. And the last one that I want to do is an example of one that has a decreased frequency. So for number 3, I'm going to do cosine of x divided by 2. This is cosine of half of x. And we're going to solve when does this equal radical 3 over 2? Still over that same interval from 0 to 2 pi. All right, right away, let's use a dummy variable. Let a equal radical 3 over 2. And therefore, cosine of a equals radical 3 over 2. Okay, so from there, here we go. Cosine is positive in quadrant 1 and positive in quadrant 4. All-star trig class. Cosine is adjacent over hypotenuse. The opposite sides would be 1s. So if I think about what's across from that 1 right there, what's this reference angle? The reference angle is pi over 6. And at this point, I'm kind of flying because this is stuff that we should be able to come up with hopefully pretty easily. All right, so what does a equal? A would equal, in quadrant 1, pi over 6. Add on the general solution, plus 2 pi n. In quadrant 4, full circle is 12 pi over 6. So we're pi over 6 before that, which is at 11 pi over 6. Plus 2 pi n, where n is an element of the integers. Okay, now at this point, I'm going to replace a with x over 2. That was the dummy variable substitution we did. Pi over 6 plus 2 pi n, and then x over 2 equals 11 pi over 6 plus 2 pi n. All right, so now to get x alone, I'm going to double both sides, right? If I want to get rid of dividing by 2, I should multiply both sides by 2. When I do that, here's what we're going to get. X equals 2 pi over 6, which was the same thing as pi over 3. And then when I double 2 pi n, that's 4 pi n now. Same thing over here. If I double both sides, these cancel, right? You get x equals, well, this is going to be 11 pi over 3 plus 4 pi n, right? The 2 would go into that 6, and you'd have a 3 down there. Hopefully that canceling makes sense to you. When I go to start plugging in values for n in just a moment, let's talk about the limit. The limit is something out of 3, since these are my denominators. Well, 2 pi is the same thing as 6 pi over 3. So if we establish that, what we can do is we can start plugging in for n. And when n equals 0, we get pi over 3 for the first solution. And we get 11 pi over 3 for the next solution. And notice how that second solution that we get when n equals 0 is already too big. So this equation has one lonely solution, pi over 3, which is why I cheated a little bit and didn't even try to get a common denominator here with these two like I did in the last one. That's typically a step I'll take. But I cheated a little bit because I knew there would only be one answer. Why did I know there would only be one answer? If you can picture what the cosine curve looks like, which is this, I want you to now picture what half the cosine curve looks like, which is just this. All right, if you cut the cosine curve in half, all you would see is this right here. When the frequency is half of x, you're only seeing half of a cos curve by the time you get to 2 pi. And I wanted to know, when does this equal radical 3 over 2? It's only going to equal radical 3 over 2 in one location, and that angle happens to be at pi over 3. So when we cut the frequency in half, we can sometimes expect to see half the number of solutions. We were supposed to get 2 answers, right, from the initial dummy variable, but in fact, when I go to solve in the end, we only get half as many solutions. The only answer here is pi over 3. Now again, there are some exceptions to that rule there, but if you're able to follow these 3, I think just with some more practice in class the next day, you'll start to really get the hang of this and be pretty good at different frequency. If this is something that you're going to struggle with though, and you try the homework and you don't get it, please reach out to me sooner rather than later, and we'll make a plan to kind of get you caught up to speed. All right, that's it for different frequency equations today. Have a great rest of your day.